Lesson 5, Pascal's triangle. Remember that mathematics is basically the study of patterns, and a really cool number pattern is Pascal's triangle, named after 17th century French mathematician Blaise Pascal. Let's take a look at this pattern and how to generate the triangle. Each row will contain a set of numbers. The first will have one number, the second row has two numbers, the third has three numbers, and so on. We are going to generate 8 rows. Let's start with the first row, which will just be the number 1. The second row will be 1 and 1. Each row after this will always start with the number 1 and end with the number 1. But how do we get the numbers in between? Let's look at row 3. We take the two numbers above from row 2 and add them, the 1 and the 1, to get 2. 2 is the missing number in row 3. Look at row 4. The second number falls in the place below the 1 and the 2 from the row above. Add them to get 3. 1 plus 2 equals 3, and write it in. Similarly, the third number falls in the place between the 2 and the 1 from above. Add them to get 3, and now row 4 will consist of 1, 3, 3, 1. This pattern continues in row 5. We look at the two numbers above and add them. So we see the 1 and the 3 will add to 4, the 3 and the 3 will add to 6, the 3 and the 1 will add to 4, so the row will contain 1, 4, 6, 4, 1. Watch as we complete rows 6, 7, and 8. We can make 3 observations from this triangle. First, there is a relation to the combinations that we have just completed. Look at the 7th row. 1, 6, 15, 20, 15, 6, and 1. And notice these numbers can be generated using combinations. We would just use 6, which is 1 less than the row 7. And we would calculate 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. This pattern works for any row. For example, if we want to find the numbers in row 10, we would use 9, which is 1 less than 10. We would go 9 choose 0, 9 choose 1, 9 choose 2, and so on up to 9 choose 9. If we want to find the numbers in row 23, we would use 22 choose 0, 22 choose 1, 22 choose 2, and so on up to 22 choose 22. Our second observation is the symmetrical pattern. For example, 5 choose 1 equals 5 choose 4. Notice the 1 and the 4 add up to the 5. We can justify this by showing that 5 choose 1 equals, using our formula, 5 factorial over 1 factorial times 5 minus 1 factorial. We can simplify this to be 5 factorial over 1 factorial 4 factorial. We can switch our two factorials in the denominator around. So we'd have 5 factorial over 4 factorial 1 factorial. And expanding it to look like the formula, we would get 5 factorial over 4 factorial times 5 minus 4 factorial, which does equal 5 choose 4. So we can see that 5 choose 1 does equal 5 choose 4. In general, n choose r will equal n choose n minus r. The third observation is just showing how the numbers are generated, as we did in the first slide, but now by using combinations. Recursive is just a fancy word to describe how we use a previously calculated value to find the next value, and we do this over and over again. Remember that each number can be figured out by adding the two numbers above. So, for example, 5 choose 3 can be determined by adding 4 choose 2 plus 4 choose 3. We can justify this algebraically by computing the left side, and then the right side, and then comparing the answers to see if they are equal. The left side, 5 choose 3, by using the formula, will equal 5 factorial over 3 factorial, 5 minus 3 factorial. Simplifying gives us 5 factorial over 3 factorial 2 factorial, which computes to 10. We could have just done the 5c3 in the calculator as well. The right side is 4 choose 2 plus 4 choose 3. So using our formula, 4 factorial over 2 factorial 2 factorial plus 4 factorial over 3 factorial 1 factorial. That gives us 6 plus 4, which equals 10. Again, we could have just used our calculator. Both sides do equal 10, so the left side equals the right side. Perfect. The general formula here would be that NCR equals n minus 1 CR minus 1 plus n minus 1 CR. Looks complicated, but NCR is just equal to the row above it, so that's 1 less than our n, and then 1 less than our r, plus, again, the row above it, so it's 1 less our n, and we use the same r. Let's revisit the pathway problem. Using the same recursive method that we used to complete Pascal's triangle, we can figure out how many ways it could take us to go from point A to point B. Using this method, we can do more complicated problems than we could by just using the combinations. For the first one, sometimes it is easier if we just turn the page so that the square looks a little bit more like a triangle, but in this case we'll just keep it straight. Starting at A, just like in the triangles, remember the first and the last numbers were always ones, so we'll fill in the ones across the top and ones down the left-hand side. For each additional point, we just add the number directly above to the number that's directly to the left. So the 2 comes from adding the 1 above and the 1 to the left. The 3 comes from adding the 1 above and the 2 to the left. The 4 would come from adding the 1 above to the 3 to the left. And we just keep repeating this pattern until you get to the end. In this case, the number would be 70. You may just want to stop the video to make sure that you can fill in this pattern before attempting the second one. For the second one, it's exactly the same thing. But notice that it gets a little bit complicated around where the 10s are. If you notice, we get the first 10 by adding the 4 above and the 6 to the left. But the next 10 to the right, there is no number above. So in this case, we are just carrying the 10 that is from the left. Continue with this pattern, and you should end up with 200 ways to get to point B. Again, you may just want to pause the video here to make sure that you can fill in this example. And Before continuing, just try the next example and then check your answer.